In this video, we're doing a quick speed run through the design of a propeller test stand. You'll get a fast but complete look at how we brought the whole thing together. This is part of the Air Pendulum project from Phil's lab. If you don't know Phil's lab and you're into PCB design, definitely check out his channel. Links are in the description below. What we're building here is a simple way to measure thrust from a propeller using nothing more than a regular kitchen scale. The idea is to mount the motor on a simple L-shaped bracket that pivots and pushes down on the scale as the prop produces thrust. And the whole test stand is designed to be 3D printed. We're designing everything in SolidWorks, and if you don't have it already, you can grab SolidWorks Maker for around $15 a month. I'm not sponsored or anything, but if you want to see how to install it, I've made a full walkthrough in another video, and the link for that is also in the description below. Alright, let's get into it. When starting a design, it's always a good idea to get a sense of scale, so we're beginning off by sketching a basic volumetric envelope, just a rough shape that the whole design will fit within. I'm also designing a simple table so we can get a reference of where everything will be sitting on as if it was sitting on a real table. And next I'm mocking up the scale that will be used to measure the thrust force. This gives a solid reference for how everything will align, and after that we'll move on to designing the base of the foot for the test rig. And here I'm sketching out the interface where our test arm will pivot. And then I'm just rounding off the end here so it doesn't interfere with our arm later. I'm also drilling through a hole for M3 screw. I'm keeping the arm design simple, just an L-shaped arm with equal lengths on either side so that the force calculations are straightforward. I'm also rounding off the corners here where the arm pivots so that it pivots smoothly and doesn't interfere with the interface. Then I create a cutout in the arm so that it starts neatly into the base interface, and we join the two parts together and test the function. So in order to measure the force accurately on the scale, we'll draw up a point geometry feature where the force will act in the middle of the scale. And to do this, we just draw a cylindrical pointed shape. You might also notice that the bottom of the surface is slanted upwards slightly so that it doesn't interfere with the edge of the scale. And next I designed the motor mount. For this setup, I'm using a simple cradle style mount, so the motor will sit in and it'll be held down with the cable ties. I'll also add a small wall in the front for the support so that the motor is kept from sliding forward. And since we are 3D printing the parts, I'll go ahead and add some fillets. When you build an assembly like this, it's really helpful to use components that are as close to real parts as possible. It helps to catch design issues early. I grabbed some realistic components from GrabCAD.com and I dropped them into the assembly. Links in the description if you're interested. And with the motor in place, I adjust the cradle size. Since we're not exactly sure which motor we'll be using yet, I'm just using an educated guess. We can always tweak it later and reprint it if needed. The motor will be strapped in with cable ties, so I'll add holes for those now. So here I've decided to make 3 holes so that we are still flexible. We can use 1, 2, or 3 cable ties if we need. Now cable ties don't technically need to be in the model. It's helpful to add them just to check the fit and also for the final render. So I add them in here and I check if they wrap around the motor properly. So to do this, I just do a basic shape and then I offset the sketch and I extrude it. So we have a basic cable tie and then we can pattern that as well. Next up, we need to add the PCB from Phil's lab. We don't want it to interfere with the thrust measurement, so we'll sit it on the flat base. Here we'll add some mounting studs and holes for the screws. So when we come to build it, we'll just drag a power cable from this PCB in the bottom up to the motor. And here I'm just doing some finishing touches to the base and adding M2 screw holes. Also adding some fillets to the interface. And lastly, we just check that there's no interference with the PCB itself and the plastic. Next, we move on to designing the propeller guard. Safety is a big priority here. We wanted the system to be safe to use, and especially when testing at high RPM motors. So we're adding a plastic guard that wraps around the propeller and bolts directly to the L bracket. To create it, we start off with a simple circular extrusion that forms the main loop of the guard, and at each end we add a vertical wall to increase stiffness and to give it some structural integrity. Then we design the mounting block in the bottom where the guard will attach. This is where we add the holes for the M3 screws. And since it'll be 3D printed, we can easily incorporate geometry to trap the nuts in place. So as I'm designing, I'm just checking that everything looks alright, and I'm adding fillets as well as I go. And here I just designed the holes for the screws. And then we're going with socket head screws from the other side. This keeps the design clean, secure, and easy to assemble. Instead of having to use really long bolts, I'm making a cutout for the head on one side and a cut in for the nuts on the other side. We're now getting to the end of the design, so I'm just going through all the parts again and checking everything looks alright and adding material to them. Then I'm also adding nuts and bolts for the assembly. This is important so that you can check that everything can actually be assembled and that it actually fits. So at the pivot point, we just use a M3 screw and we'll use the same screws and nuts in both areas to keep it simple. To use the same nut and bolt in the bottom as in the arm, I just had to add a little bit of material on either side, which is fine. I then just adjust and check everything again and make sure that it works as it should. Then I'm just cleaning up the part, adding some fillets, and now I'll move on to the drawing. The drawing is a really good place to add any important dimensions that'll be useful, and in this case it'll be, for instance, the diameter of the propeller, the height of the scale that it's designed for, and a bill of material. We can also include other important notes, such as which motor size this is designed for. We also here add callout bubbles to match it with the bill of materials. And we add a section view to make it clear which kind of bolt is used and how it's assembled. And we continue to add some critical dimensions to the drawing. Now this doesn't have to be all of the dimensions that you could do, but just the most important ones. We want the drawing to be easy to read so that anyone looking at it can quickly extract the important information. And with this, we're getting to the end of this little mini project. So lastly, we wrap up by saving everything, exporting our files to STEP files and drawings to PDF. We can also use 3D Experience to save our files in the cloud system and share them with other people. If you like these project walkthrough videos, consider subscribing to my channel so you don't miss out on new videos. Thanks for watching, my name is Raz, and I'll see you in the next one.